Thanks, Chairman. Okay, thanks, everybody. Today, I would like to introduce a joint research work between the University of Wollongong and Sydney ETCHING, Australia. This joint research work focuses on the white titan layer. We try to identify if the different traffic condition can generate different type of white titan layer, and what is the formation mechanism behind the white titan layer. And as a result, is white titan layer contribute to the squat or start formations? Oh, sorry. We focus on two types of rails. We call the rail A and rail B. You can say, okay, rail A from the passenger track, rail B from the mixed track. There's some difference for the axle load, for the curvature. But the key difference I try to emphasize is for the rail A, it's very close to the station, which means we use high braking. We call the high braking regions. For the rail B, it's just a stable traffic. So we try to identify if there are any difference between the white titan layer from the high braking region, steady traffic region. Here, we show you some surface morphology of the rail. We do the testing. Basically, rail A, rail B, from surface, you couldn't say too much difference. Both of them suffer the mild, moderate, even very severe squat defects. When we do the analysis, we try to make sure our results is trustable. So we're not testing one rail. Actually, the rail A, we choose 2 pieces, rail B, another 2 pieces. We also choose multi-point for the analysis. So we must make sure our results is repeatable. Basically, we carry out analysis by the TEM. So prepare the samples, we use FIP method. But you can see here, we focus on 2 planes. One plane is in the vertical direction. We try to check in what is changed from the top going to the depth direction. Another way, we checking the horizontal. We checking what's the change along the rolling directions. Okay, now let's discuss some results. Rail A, high braking area. Rail B, steady traffic. Top one is white titan layer. So first visualize difference, the thickness. For rail A, the white titan layer is about 50 micrometers. Rail B, stable traffic region, only 8 micrometers. It's a rare difference. Another major difference, if we focus on the transition region, we focus on the material beneath the transition. Here, for high braking regions, you see the clear initial pearlite structure, no any deformation. For rail B, steady traffic, you see the deformation texture. So from here, actually, we can see this different region, you generate different kinds of white titan layer. Now let's focus white titan layer itself. We do the analysis this time, focus on white titan layer. We try to say what is difference between these 2 kinds of white titan layer due to the different traffic condition. For rail A, this for rail B, if you observe here, first, the difference you will notice is the grain size are different. For high braking white titan layer, the size is a little bit coarse. And here, for rail B, the grain size is a little bit fine. This visualize difference. Let's say taking more details. For in the high braking region, white titan layer, it consists of plated martensite. And also you have returning austenite. We confirm the martensite, austenite by the set patterns. One more thing I try to let you be careful. When you observe the returning austenite and plate martensite, you see they in parallel directions, which means there must be a certain relationship. So the relationship between the returning austenite and martensite indicate a kind of phase transformation. For here, for real B in the steady traffic region, it consists of ultrafine plate martensite. Actually, we find some fine ferrite and fragment cementite. To determine more fundamental understanding, we analyze a small regions. Here, it shows what truly happened for the stable traffic region. You clearly show the twinning structures. This twinning is caused by the severe plastic deformation. So actually, so far, right now, we find different traffic conditions. High braking, stable traffic, you generate different white item layers. We cannot just talking TM. We need to confirm truly phase by the SRD analysis. We use a synchrotron to confirm our results. Here is a real way for the high braking region. You can see very clear. We see the austenite peaks. So it's confirmed the real A consists of returning austenite. On contrast, when you see the real B, the steady traffic, you don't have any austenite peak, but you have clear cementite peak. In addition to this, we confirm the returning austenite difference. Returning austenite for real A is 17%, but for real B, nothing. We try to do more detailed analysis. We focus on the 200 peak. You see this peak, all these two peaks, that for real A, for real B, all is asymmetrical. Asymmetrical, which means they are split into 002 and 200, which means it's martensite transformation. So we confirm, we sure this white item layer is martensite white item layer. A little bit short summaries before I move forward. Real A, for the high braking region, we found undeformed pearlite structure consists of martensite returning austenite. It truly indicate it's caused by thermal transformations. Thermal transformation is not influenced by temperature, also influenced by pressure. Pressure reduces the requirement for the phase transformation. So we call this is the TP white item layer. For real B, stable traffic, you have deformed pearlite, no austenite. The formation of martensite is caused by the carbon supersaturation. It's caused by the plastic deformation. So we call it severe plastic deformation white item layer. We know there is white item layer, but that is linking with the squat. First, let's see the field photos. A small squat sit within the white item layer. Here, white item layer looks like it's gone, but you can see white item layer still existing at the field site. We try to identify this by microscope. You see here, for the TP wells, I say it's thermal induced very thick, 50 micrometers. It's easy to be broken inside of the white item layer. Then crack going down. You see this direction. It's going down, it's vertical, because there's no texture. No. Let's be back to this. I know this morning we have lots of discussion, the start or squat. Actually, you checking this kind of white edging layer, the inducer crack structure is perfectly fit the definition of the start. This is why we believe in sinitrine, actually lots of defects is start defects. Okay, for another region, steady traffic. You see the crack will be different. This time, crack normally generate from the height of the tailing of the white edging layer. And then, you see here, it's propagate going down, going the parent materials. This time it follows the texture normally between the grain boundaries. Okay, I try to keep my time finish in 12 minutes. Let's go to my short conclusion. Basically, we find there are two types of white edging layers due to different traffic conditions. For the heavy braking regions, white edge layer containing martensite, retaining austenite is caused by temperature and pressure. It fits the definition of the start. For the steady traffic region, white edging layer have the nanocrystal martensite caused by the rolling contact fatigue. But it's not very typical squat. It's generated by the white edging layer. Both of the white edging layer play the roles for crack initiation and squat formations. So as a conclusion, I would like to thank for sinitrins for continuous support. We already do the 4-year project. Also like thanks for my colleagues, John Mcleod, Shamal, and Jonathan from the sinitrins. Okay.